The strange quark or S-quark is the third lightest of all quarks, a type of elementary particle. Strange quarks are found in subatomic particles called hadrons. Example of hadrons containing strange quarks include kaons, strange d-mesons, sigma baryons, and other strange particles. Along with the charm quark, it is part of the second generation of matter, and has an electric charge of -130 and a bare mass of 700195000000000000095 plus 5 minus 5 MeV, C2. Like all quarks, the strange quark is an elementary fermion with spin 1/2, and experiences all four fundamental interactions: gravitation, electromagnetism, weak interactions, and strong interactions. The antiparticle of the strange quark is the strange antiquark, which differs from it only in that some of its properties have equal magnitude but opposite sign. The first strange particle was discovered in 1947. But the existence of the strange quark itself was only postulated in 1964 by Murray Gell-Mann and George Zweig to explain the eightfold Way classification scheme of hadrons. The first evidence for the existence of quarks came in 1968, in deep inelastic scattering experiments at the Stanford Linear Accelerator Center. These experiments confirmed the existence of up and down quarks, and by extension, strange quarks, as they were required to explain the eightfold Way. History. In the beginnings of particle physics, hadrons such as protons, neutrons and pions were thought to be elementary particles. However, new hadrons were discovered. The particle zoo grew from a few particles in the early 1930s and 1940s to several dozens of them in the 1950s. However, some particles were much longer-lived than others. Most particles decayed through the strong interaction and had lifetimes of around 10⁻23 seconds. But when they decayed through the weak interactions, they had lifetimes of around 10⁻10 seconds to decay. While studying these decays, Murray Gell-Mann and Kazuhiko Nishijima developed the concept of strangeness, which explained the strangeness of the longer-lived particles. The Gell-Mann-Nishijima formula is the result of these efforts to understand strange decays. However, the relationships between each particle and the physical basis behind the strangeness property was still unclear. In 1961, Gell-Mann and Yuval Ne'eman proposed a hadron classification scheme called the Eightfold Way, or in more technical terms, Souflave symmetry. This ordered hadrons into isospin multiplets. The physical basis behind both isospin and strangeness was only explained in 1964, when Gell-Mann and George Zweig proposed the quark model, then consisting only of up, down, and strange quarks. Up and down quarks were the carriers of isospin, while the strange quark carried strangeness. While the quark model explained the Eightfold Way, no direct evidence of the existence of quarks was found until 1968 at the Stanford Linear Accelerator Center. Deep inelastic scattering experiments indicated that protons had substructure, and that protons made of three more fundamental particles explained the data. At first people were reluctant to identify the three bodies as quarks, instead preferring Richard Feynman's pattern description. But over time the quark theory became accepted.